Hello, and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at the basic concepts for random processes. Before I begin, though, I want to point out that the term random process has a couple of other names. Some books will refer to random processes as random signals. Some books will call random processes random signals. Other books will call this stochastic processes. All means the same thing. All the math that we're going to be doing over the next several days will apply in all cases. I prefer the term random process or random processes. Okay. So what's a random process? A random process essentially, for us, is going to be a random variable that is a function of time. For our purposes, that's the essential difference. That's probably not fully, precisely correct, but for our purposes, a random process is going to be a random variable that's also a function of time. So let me introduce the idea this way. A little thought experiment. So imagine the temperature outside your home at noon. A specific instant in time. Noon is a specific instant in time. All right? All right? We're going to measure the temperature outside your home at noon, and we'll observe the temperature for many, many days. Okay? We observe the temperature for many, many days. After collecting the temperature outside at noon for many, many days, we might be able to perform a histogram analysis. Perform a histogram analysis to fashion to estimate the PDF for the temperature at noon. All right? So in this case we have X is going to be our random variable. This is going to be a random variable describing the temperature at noon. Through histogram analysis, oops, I don't want to make that a function of time just yet. I could, through histogram analysis, through making a whole bunch of observations and performing a normalized histogram analysis, I could estimate the probability density function okay? I could do that. However, we know that temperature changes as a function of time. Okay? We know, let's put an exclamation point there, we know that temperature changes as a function of time. It's generally speaking cooler in the morning than it is at noon. It generally reaches the peak temperature sometime in the middle of the afternoon, and the coldest time of day is generally speaking sometime overnight. So what we end up with is temperature as a function of time. This will be a random process. All right, that'll be temperature as a function of time. And if we make multiple observations over many, many days of the temperature at specific times through the day, we might come up with a time-varying probability density function. And this PDF that I've notionally written here is known as my first order. That's the first order PDF for my random process. In fact, to fully specify a random process, we're going to need second, third, higher order probability density functions, but we'll get there a little bit later. Okay, so if we look at temperature outside your home at a specific instant in time, that is a random variable. If we make multiple observations over many days and perform a normalized histogram analysis, we could estimate the probability density function at noon. However, we know that temperature changes as a function of time, so our random variable is really a function of time. A random variable that's a function of time is known as a random process. And as you might imagine, the probability density function is going to change as a function of time. All right? Okay, let's talk about the notion of sample functions and what's known as the ensemble. Sample functions and the ensemble. All right. So let's keep talking about our random process, which is the temperature outside of your home. Okay. And it might make sense for us if we want to fully understand this random process. What we're going to do is we're going to go record temperature versus time waveforms over many days. Okay? These temperature versus time waveforms will be designated with a little x, and we'll put in another alpha there. Alpha will indicate for this particular discussion, let's just assume that I'm going to record temperature versus time waveforms, and I'm going to designate them in this way, little x as a function of t. Let's make that a parameter alpha, and alpha somehow indicates the day when we recorded the temperature. All right, there'll be many. This thing, by the way, x as a function, little x as a function of time is known as a sample function. Sample function. All right, we're going to record many sample functions over many days, and the collection of all possible sample functions the collection of all possible sample functions is known as the ensemble. The collection of all possible sample functions is known as the ensemble. Okay? Make sure I haven't forgot something here. All right. So in the case of a random variable, capital X, each time a chance experiment is performed, we get a result which is represented by a number. Remember that a random variable maps the outcome to a real number. So the outcome is mapped to a real number and that was designated previously as a little x. For a random process, and that will be designated capital X of t. The result of performing a chance experiment is a waveform little x of t. All right? And that is a sample function. Need a period there. Okay? All right. So let's make a couple of simple sketches here. So imagine that we go out and we look at temperature versus time over many, many days. So this will be my time axis, and say the temperature, I don't know, looks something like that. And we look at it at another day, and this is x of t alpha 2, second day, and this is a third one. Well, we know that temperature versus time could be observed over a relatively large number of days. We'll say that there's an infinite number of days since the beginning of time till the end of time. This whole collection of waveforms is known as the ensemble. All right? You'll notice that the time axis goes this way. Time axis goes horizontally. The ensemble is stacked up on top of one another. All right? So alpha 1 might represent January 1st, alpha 2 is January 2nd, alpha 3 is January 3rd of some year, and we could have, if we had thought about it, we could have recorded temperature versus time waveforms outside of your home for arbitrarily large number of years in the past and arbitrarily large number of years into the future. So let's pretend that this time right here is noon. And let's say that these are data points indicating temperature at noon. All right? You'll hear me say this phrase quite a bit. We look across the ensemble, all right? That way. Look across the ensemble. To estimate the probability density function, all right, at noon, a specific instant in time. So I'm going to look across the ensemble. I'm going to collect a bunch of data points over multiple days. I'll do a normalized histogram analysis at a specific instant in time. That gives me a random variable. Okay? Random variable has a non-time varying probability density function. However, the statistics clearly will change as time passes. All right, and so strictly speaking, my first order probability density function, and as well as my higher order probability density functions that we'll talk about later, they are going to change as a function of time. Okay? Changes as a function of time. All right. So, let's talk about some characteristics of my sample functions. Sample functions can be sample functions can be finite or infinite in number. Let's say finite or infinite in number. All right. So, for example, the temperature outside of your home might have an infinite number of sample functions. If we looked at the output of a binary number generator over 10 clock cycles, we would have a finite number of sample functions. So the output of a binary number generator over 10 clock cycles has 2 to the 10th sample functions. Now that's a bunch, but that's finite. All right, so my sample functions can be finite or infinite in number. Another thing that's important is that sample functions themselves are deterministic. Sample functions themselves in isolation are deterministic. The randomness comes in not knowing which sample function will result when we perform our chance experiment. All right, so this statement is similar to what we observed very early on when we were talking about tossing dice, for example. If I toss 2 fair dice and I create a random variable which equals the sum of spots up, there are 36 possible outcomes, and I know them all. I can write them down in a table. In fact, we wrote them down in a table. The randomness comes not in identifying the outcomes of tossing the 2 dice, but rather we don't know exactly what the outcome is going to be until we actually perform the experiment. So the results are known, the results are deterministic. The randomness comes in not knowing which outcome will occur when we perform the experiment. Same thing with random processes. The sample functions themselves are deterministic. The randomness comes in not knowing which waveform will result when we perform our experiment. I want to point out a caution here. I've sort of alluded to this a couple of times, but I want to make it just down here. I'll notice a caution. This function, the PDF as a function of time, is known as the first order. That's the first order probability density function. Just strictly speaking, to properly and fully describe a random process, I need higher order. I need second, third, fourth, fifth, infinite order probability density functions. We are going to go as high as the second order probability density function, and we'll get to that a little bit later. So alright, strictly speaking, we need higher order PDFs to fully specify the behavior of a random process. We will go no higher than the second order. I'll put a smiley face there because we're not going to get into real higher order statistics. All right, so some more properties of my sample functions. Sample functions can be discrete time or continuous time. And they can also be discrete or continuous valued. All right. So let's look at some examples of these kinds of things. So let's look at something that's discrete time and discrete valued. Okay, so let's say we flip a coin every second for 50 seconds. And if we get a head, all right, remember, a random variable assigns a real number to the outcome of a chance experiment. Likewise, when I flip a coin, the result is not a number, it's heads or tails. What I'm going to do is I'm going to assign heads to, little x of t. I'm going to set that equal to 1. If I get tails, outcomes are just words, heads or tails, I'm going to set my sample function value to -1. All right? And we will assume that my sample functions only have value at the instant the coin was flipped. We're not going to assume that I flip a coin and the value is retained until I flip it again. We'll say that sample functions okay? So strictly speaking, we would have what? 2 to the 50th possible sample functions. I'm not going to begin to draw them all out, but one might look something like this. All right, let's put a little break here, and up here is 50 seconds. This will be 1, 2, 3, 4, 5, 6, 7, 8, 9 seconds. So this is time in seconds. 2, 3, 4, 5, 6, 7, 8, 9. All right, so this will be some sample function x of t. And let's put in a designator here. That's trial alpha. And I don't know, let's say we get a +1 and another +1 and a bunch of tails, and then we get a head and then a tail and then a head, all the way out to 50, and we get a head. All right, so that would be one possible sample function out of 2 raised to the 50th power. All right, that would be a discrete time, discrete valued random process. All right. What about a continuous time, continuous valued random process? Continuous time, continuous valued random process. That is supposed to be an omega naught t plus a capital theta. Omega naught and a are going to be constants. Omega naught and a are going to be constants. Capital theta is a random variable, RV, random variable, uniform, on, let's say, 0 to 2 pi. Okay? So the randomness in this particular random process is the phase. We don't know what the starting phase is. It could be anywhere from 0 to 2 pi. This is a very important random process for us. We're going to examine this particular random process a multitude of times throughout the rest of the semester. So really what this is my random process here is a sinusoid with a random phase. Phase noise. Let's do that again. phase noise. Okay, so sample functions might look something like this. I don't know, peaks up and comes down and up and down and up and down. Another sample function might look like this, peaks up a little bit later. Those kinds of things. So let's say that's time equals 0, time equals 0. This will be the first trial. And this will be the second function, or the sample function as a function of time for my second trial, etc., etc., etc. Right? And here, I'm going to have an infinite number of sample functions in my ensemble. All right, and remember, my ensemble is that. All right, the collection of all possible sample functions is my ensemble. In the previous example back over here, I had a finite, it was large. 2 to the 50th is a big number, but it's finite. I had a finite number of sample functions, and I had discrete value and discrete time. For this particular random process, I have an infinite number of sample functions, and my sample functions are both continuous in time and continuously valued. All right, let's look at one more. Let's look at a continuous time discrete valued random process. All right. Let's use a different letter. Y of t equals, say, +1 or -1 if a cosine omega naught t plus capital theta is greater than or equal to 0, and -1 if a cosine omega naught t plus capital theta is less than 0. So in effect, what this is a hard limited version of the random process in the previous example. RP, random process. When we were talking about random variables, I used capital RV. Now let's talk about capital RP, random process. So Y of t here is a hard limited version of the random process on the last page. So a sample function here might look something like this. And we'll pretend that that is +1, 0, and down here is -1. Sorry, I'm not the greatest artist. Okay, and of course, I would have an infinite number of sample functions in my ensemble. Okay, infinite number of sample functions in my ensemble. I'm not going to try and do an example for a discrete time continuous valued because the pictures kind of get a little complex for me and I have a hard time drawing them out nicely and neatly. All right. That is all for right now. Just a short introduction to some of the terminology associated with random processes. We'll pick up more in the next video lecture or two and continue our introduction. And as usual, if you have any questions, please contact me at your earliest convenience and I will answer them as fully as I am able. Have a nice day. Bye-bye.